just going to revisit solving quadratics now that we've got this new number that we can deal with. Okay, so x squared plus 3x plus 7 equals 0. Well, we know we can't do what multiplies together to give 7, adds together to give 3, doesn't work. Throw it into the quadratic formula and we come up with this problem, the square root of negative 19. Well, it used to be a problem, but now it's not a problem because we can simplify that surd, because that's the same as saying the square root of negative 1 times the square root of 19. In other words, it's the square root of 19i. Some people prefer to put the I in front of the square root sign so it doesn't look like you're saying square root of 19i. Okay, so we have two possibilities. But now, every quadratic can be done by completing the square, because every quadratic can now be written as the difference of two squares. Yes, that says plus 19 on 4, but I can rewrite that now to make it the difference of two squares by saying, oh no, I don't have plus 19 on 4. What I've got is minus 19 on 4i squared. It becomes the difference of two squares, which we can do quite easily, and there's my solution. It's obviously the same as I did it the other way. So every quadratic now we could do that, and if the numbers are nice, that could be quicker. So let's create quadratics. Here's an interesting fact. Every quadratic where the coefficients are real, the solutions will be conjugates. And that's because of the quadratic formula. Remember, it's plus or minus the square root. You're always going to get conjugates. In fact, it's true for all polynomials, not just quadratics. In all polynomials, they'll appear in conjugate pairs. It's all right. If I had factorised it then, I would get x minus some number, and then x minus its conjugate. Expanding that out, we see what we get here. The middle term here is z plus z conjugate. And if you add a number with its conjugate, the imaginary parts are going to cancel out. You'll end up with twice the real part. So we've got minus twice the real part. And then the product, z conjugate, remember that's what we saw was the sum of two squares. If I want to create the quadratic equation then that has roots 4 plus I, 4 minus I probably wouldn't write this down because I'd just look at it and do it, but the sum then is 8. See, the imaginary parts cancel out. The product, sum of two squares, 16 plus 1, 17. So there's my equation. X squared minus 8x plus 17 is equal to 0. Finding the square roots of numbers. And obviously we know how to find the square root of real numbers, but what about other type of complex numbers, ones that aren't real? Well, let's say a plus ib is going to be the square root of our complex number. I could square both sides and create an equation. I know the real part must equal the real part and the imaginary part must equal the imaginary part. So, if the square root of x plus iy, if its answer is a plus ib, I know that a squared minus b squared must be the real part. And I know that 2ab must be the imaginary part. Let's do this one. Square root of minus 12 plus 16i. A squared minus b squared will be the real part. 2ab will be the imaginary part. I've got simultaneous equations. I'll make b the subject of the second one, substitute it into the first one, and we end up with a quartic. But the beauty of this is any quartic we create here will actually be a quadratic. A to the power of 4 plus 12a squared minus 64. So what multiplies together to give negative 64, adds together to give 12. We've got 16 and negative 4. So either a squared is 4 or a squared is negative 16. A squared is 4, we get plus or minus 2. Substituting back in for b, I'll end up with plus or minus 4. A squared equals negative 16, no solutions, no real solutions. But, remember we said the imaginary part and the real part, they're both real numbers. So I need a real solution for this. A squared equals negative 16 doesn't concern me. And there's my answer then. The square root of negative 12 plus 16i is plus or minus 2 plus 4i. Again, there's where the difference comes in. If I'm just finding the square root of a real number, say I said, what's the square root of 25? Right, it's just 5. It's not plus or minus 5. But when we're dealing with complex numbers, we say plus or minus, because you can't order the complex numbers. So plus or minus 2 plus 4i is the answer. Well, I think there's an easier way myself. There's lots of different ways you can do this, by the way. But have a look at this. Same thing. And remember, we just found out that a squared minus b squared is the real part and 2ab is the imaginary part. if I play around with that, x squared plus y squared would end up being, after a bit of algebra, this expression here. A to the power of 4 plus 2a squared b squared plus b to the power of 4. But that is a squared plus b squared squared. So in other words, I think a neat way of doing this, square root of x plus iy is a plus ib, then I know the difference of two squares will always be the real part. The sum of two squares will always be that square root of x squared plus y squared. How do we tell about the signs? What you do is you look at the imaginary part of what you're finding the square root of. If the imaginary part is positive, then a and b must have had the same sign. So remember, 2ab is equal to the imaginary. So if that's a positive number, they both are either negative or they both are either positive. But if y is less than 0, they must have had a different sign. Again, if 2ab is a negative number, one of them's got to be negative, one of them's got to be positive. That's how we can tell. So if I do the same question, now I'm going to say the difference of two squares is negative 12, like I did before, but now I'm going to say the sum of two squares will be 20. 12, 16, 20. Pick some nice numbers there because it's a Pythagorean triad. It makes the 20 nice and easy to work out. Simultaneous equations, I get 2a squared's 8. A is 2. I don't worry about the plus or minus 2. I always just take the positive number. Okay? So A is 2. Why? Because if I take A to be the positive number, I know B will always have the same sign as the imaginary part in this one. So I know B is going to equal 4. It's going to have the same sign. The imaginary part is positive. Therefore, there's my answer. And because I'm doing plus or minus anyway, that's why I didn't worry about the plus or minus on the A. I always just set the A to be positive, and then I'll have a look at the imaginary part of what I'm finding the square root of. And if that's positive, it'll have the same sign. If that's negative, it'll have a different sign. There's my answer. Let's try this one there. A little bit more involved because we don't get a Pythagorean triad on this one. You can't go 4, 5 and get a nice neat number to become a Pythagorean triad. So a squared minus b squared is 5, but a squared plus b squared is the square root of 41. Okay, let's eliminate the b squareds and I get this wonderful expression for a. It's a half of the square root of 10 plus 2 root 41. That's a number. Substitute back in to work out b squared, and b ends up being, oh look, the imaginary part is negative, b is negative. Different to the a. So I get a half the square root of negative 10 plus 2 root 41, meaning my final answer for the square root of 5 minus 4i is this beautiful expression, plus or minus a half, root 10 plus 2 root 41 minus I, roots negative 10 plus 2 root 41. There are some people that would freak out at that sort of answer, but it's a number, it's just a number. Let's solve this quadratic then. What multiplies together to give 2 minus 2i adds together to give 2 plus i. Alright, let's just go to the quadratic formula. Okay, go to the quadratic formula. Oh, I now need to find out the square root of negative 5 plus 12i. Okay, difference of two squares will be negative 5. Then a squared plus b squared will be 5, 12. This one is a Pythagorean triad. That's going to be 13. A turns out to be 2, therefore b ends up being 3 when we substitute back in. Notice the imaginary is positive, so b is positive. Okay, now we just tidy this up. I end up with two answers there, I or negative 2 minus 2i. Now you might have spotted that. Remember I said what multiplies together to give 2 minus 2i adds together to give 2 plus i. Well, you might have spotted that. Probably you wouldn't. So we'd go through our quadratic formula. So that's finding the square root of our complex numbers.